Hi, this is Brahmesh Jain from Arizona State University. In this video, I'll be giving a presentation on one of the assignments from embedded system programming. Let me quickly go through the assignment problem. You can pause the video and read this assignment problem. Assignment involves programming two devices, namely 8x8 LED matrix and an ultrasonic sensor for distance measurement. Okay, the first part of the assignment is writing Linux driver for those two devices. Let me show you the output so that you get a good understanding of the requirements. See, if I move the object closer to the distance sensor, then the dog runs faster. If I go back, then the dog reverses its direction. If I go front, it runs faster. This is how the output should look. Let me explain you how the distance measurement is done. First, you need to send trigger pulse like this onto the trigger pin of the distance sensor. Then it replies you with echo signal whose duration is proportional to the distance between the object and the sensor. So for this, you need to make one of the GPIO as output for the trigger pulse and another GPIO as the input to read the echo signal. To communicate with the LED display, you need to send a lot of SPI commands to the LED matrix. Let us see what all commands we need to send. This is the data sheet of the MAX7219 LED driver. It has number of registers. There are some 14 registers, out of which last 5 are for the setting of the LED matrix. The first one is the decode mode. This tells you whether you need BCD decode or not. In this assignment, we don't need BCD decode, so we need to send a particular value for that register. Here, say, you can see we don't need a decode, so you need to send 00 as the data for this command. Next, you can set the intensity of the LED. Then you can set the scan limit. The scan limit is like this, whether you need to display all the rows or not. Shutdown register, you can program it to shut down the entire LED display, and display test, whether it will be useful while debugging. Then let us see how we need to send SPI command for this display driver. It consists of 2 bytes. The first byte is for the data, D0 to D7, and the lower nibble of the second byte has the address of the register for which you need to put this data to that register. The LED matrix has 8 rows. Each of these 8 rows is represented by these registers, digit 0 to digit 7. So if you want to switch on all the LEDs in the first row, then you need to send FF to this register. Similarly like that. Okay, the user application consists of 2 threads. One is called the distance thread and the other one is called display thread. Distance thread continuously communicates with the GPIO to send trigger pulse and receive the echo pulse. In short, it takes care of distance measurement. And the second display thread communicates with SPI dev and sends all those commands which I told you earlier. Let us see how sensor thread work. This is the flow chart for the sensor thread or the distance thread. You start the measurement by sending trigger pulse, make trigger as 1, then go to sleep for 10 to 15 microseconds, then again make the trigger as 0. I'll show you how it is done in the code. You send 1 to the trigger pin, then go to sleep for 12 microseconds, then again make the trigger pulse as 0, then wait for the rising edge on the echo pin. As soon as the rising edge appears on the echo pin, this function returns. Then you need to take the timestamp, you need to capture the timestamp. As soon as it returns, you take the timestamp here. Then make the edge detection for falling. We have detected this rising edge, then we need to detect this falling edge. So make this as falling. Then again go for pole. As soon as it detected, then you need to, okay, you are going to pole here. Then when the falling edge appears, then the function returns, then you take the timestamp again. We have captured the rising time and the falling time. Through this we can know the duration of the echo pulse. By multiplying a factor with this duration, we get the distance like this. The factor might look like this, 7.5 by 20,000. This will convert this duration of the pulse into millimeters. Okay. Then make the echo pin as a rising edge so that it will be useful for the next measurement cycle. Then you go for sleep for a longer duration, like 50 millisecond, 100 millisecond. This will decide the rate of measurement of the distance. After coming out of the sleep, you check for the timeout, whether this thread needs to exit or continue processing the distance. I'll show you in the code. This is where you check for the timeout. This timeout will actually be set by the main thread. Yes, the threads are created here. Then the main program goes to sleep. Then it sets the timeout flag. This is how the sensor thread works. After sensor thread, we will go to display thread now. In display thread, first you need to initialize the display. This is done by setting those registers which I told you earlier. As you can see in the code, these registers are set here. This will test the display. This will switch on the entire display once and again switch it off after some 10 millisecond. Then you set the decode register, then the intensity register, then you set scan limit, then you make the shutdown register as normal operation. Then you clear all the digit registers, digit 0 to digit 7. This is the display init part. Next, you read the distance. This distance is a global variable which was updated by sensor thread here. You read that distance, then decide whether you need to move to the whether the dog needs to move to left or right. You compare the present present distance with the previous distance. Then you decide whether you need to move to whether the dog needs to move to right or left. In either case, I will be displaying the standing still picture of the dog. Show in the code. This is the still picture of the dog, where depending on the dog direction, I will be considering two different arrays. These are the arrays which are declared earlier. As you can see here, there is a frame for dog still picture, and direction is right, and dog run towards right, dog still towards left, dog run towards left. So for the first part I'll be considering this dock still. Next I'll go to sleep, which is sleep for a duration which is proportional to distance. Say for an object is very near to the sensor, then the distance will be very small, so you go for a shorter sleep. After coming out of sleep, now we need to display the running motion of the dog. So similarly, you display the running motion of the dog. Then you sleep again. You slept the same amount you earlier slept. Okay, now test for the timeout. This is one frame is done, one sequence is done, so now you test for the timeout. This is similar to the timeout which was in sensor thread. If the timeout has not happened, then continue with the same process. If the timeout has happened, exit the thread. The entire thing I explained so far is related to first part of the assignment. Let me show you the output again for the first part of the assignment, so you can relate everything together. Now you can see if an object is very closer to the sensor, then the dog runs faster. When you move back, then it changes the direction. Since the object is very far, it will run slower. When the object is again very closer, it runs faster. This is the first part of the assignment. Having done the first part of the assignment, let us see what the second part of the assignment is. The second part of the assignment is about writing drivers for these two devices. The first step of writing device driver is first defining the capabilities of the driver. A driver for a sensor would probably have capabilities like to trigger a measurement from the sensor, and another capability should be to read the measured data. Similarly, in this driver, first we trigger the measurement by making a system write call, and then we make system read call to get the measured distance. In this driver, in the write function, we first create a thread that looks after the measurement. This is done so because the write call should be non-blocking. Let me show you in the code. You can see here, as soon as there is a write call to the driver, if the driver is free, if there is no ongoing measurement, then we will create a thread and run it. If the driver is busy, we will return -1. Then let's see what does this thread do. Similar to the user application, first it should trigger the pulse on the trigger pin, and this is done via GPIO lib module. You can see here, this is the pulse measurement thread, and you can see here, first it creates a pulse of width 150 microseconds. Then it waits for the completion flag. This completion flag will be set only after we receive the echo pulse. So what happens when it waits for the completion? An IRQ will be called from the echo's rising edge and falling edge. You can see here, this is the IRQ for a rising and falling edge of the echo pulse. If it is rising edge, it will take a counter value. This is done by RTDSE time counter. Then it will take the measurement start value, then it will set the edge detection to falling. So next time this IRQ is called, it is for sure it is for the falling edge. So that time we are going to take another counter value and store it as measurement end time. So now we have two variables, rising timestamp and falling timestamp. So when the user application requests for the measured data, then it will make a read call. This read call is going to come here. This is the read call, and then we're going to find the pulse width by subtracting the start time from the end time. Then we are going to divide by the frequency of the CPU, so we will actually get the distance measured in millimeters. This is returned to the user application. This is how pulse driver work. Okay, let me now explain the second driver. Second driver is the display driver. First, let us see what all the user application expects from a display driver. A display driver should be capable of receiving a frame and also the time period for which this frame has to be displayed on the screen. So for this, for example, if we want a frame which has to be displayed for 200 milliseconds and a second frame for a 300 millisecond, then the user application has to continuously call frame with the time period. It makes a number of system calls. So hence, this is not a feasible solution. We have defined a feasible solution where we will receive a pattern, a number of frames, which is like patterns. And we have defined a buffer of 10 frames. So user application can send all the 10 frames together, then send the sequence in which the frames has to be displayed on the display. For example, here you can see frame 8 is first the frames are sent, frame 0 to frame 9. Then the user application can request to display frame 8 for 200 milliseconds, then frame 5 for 100 milliseconds, and so on. The end of the frame is represented by 0, 0, frame number 0, and display time is 0. Let me show you in the code. In this driver, IO control function will receive the number of frames. As you can see here, a 10 cross 8 array is received by the IO control function, and it is copied to a pattern buffer. This pattern buffer is defined in the device structure, as you can see here, and device structure also contains a sequence array which is 10 cross 2. Since the time can be more than 256 milliseconds, hence I have defined the sequence as the unsigned short. Next, through the write command, the driver receives the sequence in which the frames are to be displayed on the display. Here, as you can see, through the buffer it will receive the display sequence, and you copy all the sequence one after the other, and then you create a thread to display that sequence. This is done because we need a non-blocking call from the user's perspective. Then it creates a thread. We'll see what this thread does. In the meantime, if the to see if the user application can see whether the displaying all the frames are done or not through the read system call. The read system call will say whether the device is busy or not. So you can see, very simple. It just reads the flag and say whether it is free or not. Let me explain you what this display thread does. It reads the frame sequence, whether the frame is 8, 5, 4, 3. It finds the respective array index from the pattern array, and then it will send that frame. Say here frame number 8. Frame number 8 will be sent. This frame 8 will be sent, and it will go for the sleep for 200 milliseconds. Then after it wakes up, it will send the second frame number 5. Then frame number 5. Afterwards, it will go to sleep for 100 milliseconds. Like this, it will continue till the end of the sequence with a 0 and 0. To explain this, I'll show you. You can see this. This is responsible for sending the frames. You can see this macro definition. This macro is responsible for sending for communicating with the SPI core and sending the frames. Here we are initializing the message, then we are adding the tail, adding to the linked list where the SPI messages are sent. Then we are waiting till that message is sent. The SPI sync is the blocking call, so it gets blocked at this call. That's it. This is how the SPI LED driver works. Having written both these drivers, that is SPI LED driver and pulse driver, I was very excited to write a simple application wherein we can test both these drivers and give a distance control display. Let me go to the application. Now, before that, I'll play the output of this application, so you get to see what I'm doing. You can see here there is a moving alphabet ESP. Let me explain how this is done in the application. This is the user application. It will create a thread called distance measurement thread. This will continuously communicate with the sensor driver and gets the distance measurement and updates on this global distance. So here is the distance measurement task. It will trigger the measurement, then it will read the measured value. Then I have created ESP display thread. This is just an application to display. It is not distance control. It is just an application to display a moving text. As you can see here, the pattern contains 23 frames. The frames are sent. 10 frames are sent. Then a write call is called to display that sequence. Then the next 10 frames are sent. Then again a write call is made to display that sequence. Because it is 23, then the last one will have 3 frames and display for 3 frames. This is the part for displaying ESP. Okay, I'll continue the video. This application is distance controlled. As you can see, moving car. When an obstacle comes in front of the car, then the car suddenly stops. This is a simple application that you can say not so advanced collision avoidance system. that are used in vehicles. As you can see, the car goes very slow after an obstacle is found. Now, as soon as some obstacle like a child coming in front of a car or any animals going in front of the car will stop the car. We'll see how this was done in the code. This is the thread that does this. These are the pattern that creates the motion picture for the car. As you can see here, I have two sequences. One is to make the car run faster. The other one is to make the car go very slow. As you can see, the speeds are having a lot of difference. The car default slow speed is 2000, whereas the fast speed is 150. This is the display time for which that frame has been set. Here we read that global distance value and see whether it is the minimum stop distance. Then based on that we will send either slow sequence or fast sequence. That's it. This is how the driver and user application was written. To summarize, first I wrote user application to display a moving, running or walking dog. Then I wrote two drivers, one for the sensor and another for the display. Then one more user application to test these two drivers. I would like to take an opportunity to thank Professor Jain for giving us such a wonderful project to work on Intel Galileo board. Thanks for watching this video. Have a great day. Bye.